I think the same group. By the way, this design was done by the National Tsinghua University in Taiwan. So the same group improves the design from AT2R to be 71R. So I will not go into the details. So this is published in VLSI 15. So here the difference is get rid of one of those branch of the R1 because they realize that if you only have one R1 cell, you can do the same function because of the asymmetry between the Q and Q bar. You just need to store the information to one R1 cell. It's okay because this asymmetry, if this one is high resonance state or low resonance state, then the Q, if Q is restored to be 1, then Q bar must be 0. So you can save one branch. So this will make your SRAM cell even more compact. Okay, one reason that when this one is not used is because for the SRAM, it's really challenging. Not challenging, I mean the industry would not prefer to increase the cell size, even from 60 to 70 to 80, right? So we talked about the 80 SRAM cell before, and you have that homework, but that one is not widely used. Also, it can improve your noise margin, right? The same here, right? So here you add 2T, then your area increase. So it's not good.
So do we prefer power gating like for SRAM or do like use state for SRAM?
Do what?
Like when we are turning off our power domain, so will we do a power gating for the SRAM also or just use the state of SRAM?
We prefer to do this power gating for SRAM, right? So what's your question?
Yeah, I mean, not in this terms, like by using a header switch or a power footer switch.
For the others,
so we can do the power.
So you can extend this design to flip-flop as well. Yeah. So for flip-flop, you can also have the local memory and then have the data stored in your non-volatile memory cell. Yeah. So in those logic, you always have the flip-flop, right? So actually, in the research community, there are many proposals for the non-volatile SRAM cell with different circuit topology, circuit combinations with different number of transistors and different, mostly with 2R, 2 resistor. Of course, this resistor can be RRAM, can be phase change, or can be STT. They have some subtle difference in terms of the resistance and on-off ratio. But in general, you can have those kind of designs. I'm not going to the table of this one. And if you're interested, you can read this table and take out the differences. So I think some earlier prototype, there are some challenges in the DC leakage. They call it DC short current. So basically, you have some DC path from VDD to ground. Then you are always leaking, so it's not good. And later, what we talk about so far is, I think, is this one, 282R, and the second one is the 71R. So those are regarded as better designs, and you can check this if you wish. So I would say that if you came up with some new designs, I'm not surprised because there are many possibilities here. So you can make some cells and then write a paper. I think no problem. But the question, as you mentioned before, you asked before, are this going to be used in the real product? Then I think the key challenge is still if the application really needs this no power feature or not, and also are the technologies mature enough or not, right? So the reliability is still a concern. So this is a non-volatile SRAM. Any questions? And then we talk about the TCAM application. So what is a TCAM? It's short for this ternary content addressable memory. Okay. So typically it's used for data pattern match. So pattern match operations. So the TCAM and run, let's say CAM and run, is a twin of sisters. The CAM versus run. So anyone knows the difference between a CAM and the run we talked about before? Any idea? We talk about SRAM, DRAM, run, right? Random accessible memory. So the input for run is let's say the input is the address bit. You give address to the run, and then you get the data out. The CAM is just the opposite function. You give the CAM the data, and then it will return the address to you. So then you can find whether this data is stored in this CAM or not. So it's good for the pattern match, whether you have this pattern stored in this database or not. So it's a search process, and it can enable this parallel search. You have some feature or pattern you want to search in some database, then you store that database in the CAM, and then you have the input data to the CAM, and then it will tell you whether this data is in this database or not. So this is the application for the CAM. And the TCAM, okay, this ternary stuff is because you have this don't care condition. Okay, so this is let's say a very simple organization for the TCAM. As we discussed, is the input is the data you want to search. For example, in this simple example, your data you want to search is 1011, and you want to know whether this 1011 is stored in this pattern or not. And then the output is the address of the data if it's in the array. So then you save many data in this TCAM, and some of the data is X. Okay, X means don't care. It can be 1 or can be 0. So you just need to search whether you have this 1011. So you look at this. The first row is a match. Okay, because the last one is X, can be 1 or can be 0. You see, it's a match. And the second one, this one is different, so it's not match. So it can return you which one is match, which one is not match. If it's match, then what is the address? So to implement this function, okay, if you use the CMOS technology, you need for each box there, you need 16 transistor. So it's called 16 TCAM cell. And this is a circuit schematic. So essentially, you have two SRAM cells here. This is one SRAM, and this is another SRAM. And the reason you have two is because you have to implement this X don't care condition. So the idea is that you are going to have the complementary search data. For example, the second one is 0, so that means this is 0, and the search name bar will be 1. So those two will be input to the gate of those two transistors. And then, depending on the data pattern, you store here. For example, if you store 0, then means here you are going to have 0. And then, oh sorry, this is 0 and 1. This is always complementary. Okay, this is 0 and 1, and 0 and 1. So the data you store here, okay. If it's 0, then this SRAM cell, this Q will be 0, and this one will be 1. Okay. If it's 0, then will be complementary. So if you have those pattern, you look at this. So this is a pull-down network. You have two transistors in series, and both gates are on. So you will have discharge current to here. So this node is pre-charged to be VDD. Now you have discharge through this branch. So then the output here will be low, and through the inverter it will be high. So that means what? That means it's a match. The output give you 1, then it's a match in this case. And if you want to implement a X condition, you don't care, okay? So then you can have both of them to be like 0, I think. Both of them be 0. Then you can implement the match condition. So this is how you do this TCAM with SRAM essentially, with some pull-down network. Of course, this cell is very large. You need 16 transistors. And then the question is, if you use emerging memory, can you make this smaller? And also, you can make this non-volatile, right? Because SRAM is volatile. Then the database on the SRAM cell, is volatile. Once you power off, then your database is gone. So every time you need to load in the database from somewhere, from the flash, for example. So if you can build in the database into the non-volatile memory version of the TCAM cell, then you can turn on it right away and then do the search. So here is one design by the same group. It's called 4T2R Non-Volatile TCAM. So the design is like this. Again, this is the pull-down network. You have two complementary kind of pull-down MOS. Those are controlled by the search bit, for example here, or your data line. This is data you want to search. So for example, if this is 1, this is 0, so this is the data you want to search. And then you can program your memory cell state. Right? So here, if it's in the, let's say, low reason state, this one is in the high reason state, then you see this one, this is a pre-charge to be VDD. So if the data pattern is like LRS and HRS in this way, so this current will flow here, right? Because this transistor is on, and this is low reason state, then current can flow through. Then this will be pulled down. So that means you find some pattern here. But if you reverse that, if your data pattern you want to, or let's say if the data you search is different, 0 and 1, in this case, then this path will not be on because this transistor is off. And in this case, this transistor is on, but this resistance is high. So the current flowing through this is small, so this will not be pulled down too much. So then this is not matched. So basically you compare your input data with the pattern you store in those memory cells, and whether you have a discharge path or not will determine the output. So this is the design of this 4T2R non-volatile TCAM. So if you want to implement the X conditions, then you just need to have those two the same state. Then no matter what, they will give you the same output. That is the X condition. So this is the TCAM cell. Any questions? And again, this is verified by this 180 nanometer CMOS technology with this half-offset R1 process. And the search delay is like 1.2 nanosecond if you want to search some bits. Here it didn't say how many bits, but I think 32 or 64 bits basically. You want to search from a large database, whether you have the certain 32 bits or 64 bits in that pattern, then it can return you the answer with like 1.2 nanosecond. So this is here is word length, how many bits you have to search in parallel. So even it can support up to 256 bits search in parallel. And I think later there are some progresses in this design by reducing the number of transistor and resistor to 3 T1R design. And it's still, again, this is the non-volatile TCAM. And in this particular case, it used 3 resistance levels for the ternary data you store in the R1. So now the R1 is not just the 0 and 1. It has 3 resistance levels. So basically the high resistance state, HRS, stores 0, and the LRS stores 1. And then there's a middle resistance state, MRS, stores X, don't care. And I will not go into the details here. You can read the truth table here, and you can figure out why only certain combinations of your search data and the stored data, when they match, then you will have discharge current here. That is how you find the data.
Are all of these papers simulations?
No, all of them I show you is cheap.
So these transistors are able to give enough current for the original forming of the filament in the RN?
Yes, those are old technology transistors. You see 180 nanometer. Yeah, but in principle, I mean, once today's RM, for example, TSMC offer you 40 nanometer, Intel offer you 52 nanometer, so you can migrate the design to these platforms. So no problem. Yeah, I don't show you the simulation papers because I don't believe in that at all. Okay. So what I showed you is all verified by silicon. It's a chip. Whether the chip is on the market or not, that's a question mark. Okay, but at least it's working in the silicon.
So the R has to be vertical, like to the higher metal layer, because the reason is
so your R is always in the higher metal layers, right?
yeah.
So different companies may have different metal layers to integrate the R. Some of them integrate between metal 1 and metal 2. Some of them integrate them between metal 3 and metal 4. Yeah, but they're all above the transistors. So literally, they don't occupy too much space for you. But you need to add additional transistor for the SRAM case. You add 2T to the 6T, become 8T. That is the area penalty you need to pay for. So R itself is on top, so it does not really occupy your space. Okay, so this is this design, and here are some measurement results. I will not go into the details. This is this is called the Schumann plot, similar as the SRAM. And you can vary the power supply, and then look at the delay change as a function of the power supply and the pass and the fail, and then you can draw the envelope of this pass and fail boundary. And in this case, you can see that it reach even below 1 nanosecond search time at 1 volt. Of course, when you reduce the power supply voltage, then your delay will be longer. This is pretty fast. You can search a database, large-scale database, within like 1 nanosecond, or less, like 64 or 28 bits. And again, there are many designs, okay, possible for this non-volatile TCAM. And there are many proposals by different groups with different technology. Some of them are using phase change, some of them are using STTM run, and some of them are using run. And there are pros and cons for each of the designs as listed here. I will not go into the details. But I would say that for the TCAM applications, because you don't need to write the TCAM cell very often. If your database is not updated, the database is just by one-time programming there, then the endurance is not a big problem in this case, because you don't need to write very often. So then the run is okay, at least from the endurance point of view. But again, the variability, reliability still are the concerns for those designs. Okay, so summary. Beyond the memory applications, I think the non-volatile memory will find some new applications in the logic domain because it is compatible with the backend of the LAN fabrication process in the metal layers. And as embedded memory, it provides the non-volatility to your logic. So those non-volatile SRAM, non-volatile TCAM, non-volatile flip-flop, right? So you can, if this is doable, then you can enable this low power dynamic power gating for your chip. As I said, endurance is a problem. How often you do this power gating?